Welcome back, everybody. If you didn't get a chance to watch the little mini videos on 6.2, 6.3, watch them later. They're gonna like walk through where these formulas come from. 6.2, we're gonna dive into some examples here. It's doing volumes by slicing. And it's the disc washer method. And both 6.2, 6.3, and a lot of stuff in actually 6, a lot of these stem from revolving or rotating a function around an axis. Or how is that still so bright? I'm gonna blind you guys. Shit, maybe if I just point it straight downward and just use regular light. That works. All right, so we got some graph here, some f of x. Let's say we rotate it around the x-axis. So this is making a circle like this around that. And different height up here makes a larger circle there. Over here, even bigger. And so you end up getting this crazy looking shape. And the disk method involves going, if we're integrating, if we rotate around the x-axis, we're doing little disks like this. This disk from the side is a circle. A disk from the side. So like a circle like that. The volume of the circle, or this little tiny circle, is going to be pi r squared times the height, but the height here is a like infinitely thin thing. So like a dx in this case. So that's how we're going to do it. And it also works if we're rotating around the y-axis. We have a function and we rotate around the y-axis. We're doing disks this way. So our disk will have a dy height, and we're still doing pi r squared. So let's set up a little example here. Let's do y equals e to the negative 2x. And we're gonna use boundaries of y equals 0, x equals 0, and let's do x equals 1. And we will rotate around x. So sketch it. E to the negative x goes down like it goes down from left to right like that. That's y equals e to the negative 2x. And y equals 0 and x equals 0 are axes. We'll do x equals 1 right there. So this is the region we're wanting to rotate. So if I rotate it around, looks like the side on the left is going to make flourish, sweep out this big circle. And it's going to look like a little bit like a nuclear power plant kind of thing on its side. That's my attempt at doing a 3D sketch of like what it's going to look like. We're going to do little discs right here. So a little disc from there. Put my axis in there. And that is like doing this part right here. But it kind of helps if you have like a sketch of it. That shows me what R is. So R looks like it's going up and down. R looks like Y. So this disk is going to have a pi y squared dx. The dx is the width. That's before plugging anything in. Does that make sense on like where this is coming from? Pi r squared. We have a little circle here. The radius is going up and down until it hits the axis. So that's y. Y of this one right here, y equals e to the negative 2x. It's hitting that line right there. And then our height is really going that way. It's our dx. So if I write this in terms of, I don't want to use y, I want to use x. So I'm going to use e to the negative 2x. We'll have pi e to the negative 2x squared dx. And it looks like we're going from 0 to 1. So this is my y squared right here. If you're having a hard time picturing what's going on, picture a fan that is not moving, like the blade is like a rectangle. Maybe make it square, not like oblong. And as soon as you turn that motherfucker on, it spins so fast the fan looks like a circle. That's what this is from the side view. It's making the circle the same way a fan would, but when it's off, it's just fucking rectangles. So that's really what's going on. If with this, the fan only had one blade kind of thing. Does that make sense? Does that help like visualize it? Okay. So this ends up being e to the pi e to the negative 4x dx. And so when we integrate it, we get pi over negative 4. It's still e to the negative 4x. And we're evaluating from x equals 0 to x equals 1. If you're not comfortable with doing that in one step, you can say u equals negative 4x, du equals negative 4 dx. So dx equals 1/-4 du. And change that integral to pi/-4 e to the u du. And you need new limits. This goes from 0 to -4. But still, the pi/-4, if we switch back to x's, we have that. So I have pi/-4. If I stick in the 1, I've got e to the -4 minus e to the 0. And that's 1 right there. If I move the negative inside, it just changes the signs of these. And I will get pi/4 times 1 minus e to the -4. You can win a freehand sketch that little fan up there. Fan with one blade. And as you turn it on, it spins super fast and it looks like a circle. You should be showing this kind of work. Do not go from this to the answer. That means you did it on a calculator, and I'm not testing how well you use a calculator. This is testing how well you learn calculus. Otherwise, someone that has an expensive calculator has an unfair advantage in this class, and that's not how this works. You're supposed to learn calculus. Just letting you know. Any questions on that one? Does anyone need it up longer? All right, onward we go. So next one, let's do on this one, we're going to do x equals 1 minus y squared. And we'll have x equals 2 plus y squared. And let's do y equals 1 and y equals -1. So before I put them on the grid, just as a reminder of how A goes. Well, B is easier to show first. Y squared goes to the right like that. And the +2 shifts it right 2. And negative y squared is going to open to the left. And the positive 1 in front of it is going to shift it right 1. I didn't tell you what axis to rotate around. We're going to rotate around y. So let's sketch it. This is the 2 plus y squared. And 1 minus y squared is going this way. So these actually don't intersect. So we'll just say this is at y equals 1. And this is at y equals -1. And that's going to get rotated around the y-axis. So we'll have something like this here. And black is going that way like that. So between those two and y equals 1 and -1, that's kind of like what we're looking at here. Maybe I should throw in x equals 0 to make it clear that we're stopping at the x or the y-axis. And we rotate it around this bad boy. So our discs are going to be like this, and it doesn't look like they're going to be a disc, they're going to be like a washer. So an overhead view of that one gives us something like this. With an outer radius and an inner radius. Now, if I use big R for the outer and little r for the inner, the area of this washer here is pi big R squared minus little r squared. It looks like we have, our disk has a height of this, so it's going to be a dy thing. We're looking at a dy, which means we want r's in terms of y. And so we need to identify which of these functions is the outer function and this is which is the inner function. If we're looking at this disk right here, as that sweeps out, the outer one is here. And that was our 2 plus y squared, which is conveniently already in terms of y. That's handy. And our inner one was this line right here. That was also in terms of y. That was 1 minus y squared. So it looks like we're doing -1 to 1. That's our y range. And then we've got pi. Our outer r is 2 plus y squared. And it has to get squared also. Don't let the square and the y trick you. Minus our inner r squared, 1 minus y squared squared dy. All right, I'll put the pi outside. -1 to 1. Something squared is the first one squared plus double the product plus the last one squared minus. Same thing on this one. Anything squared is the first one squared minus double the product plus the last one squared. Yeah,
You said -1 to -1?
yeah. Because we're going from here to here. So all the way up. I mean, we could have tried to do some substitutions, but I don't know that it's gonna work well. I don't know what we would substitute for. It's easier to just multiply this shit out. Let's put shit together. 4 minus 1 is 3. 4y squared plus 2y squared is gonna give us 6y squared. And it looks like the y to the fourth goes away. So we integrate, we got 3y plus the y goes up to a cube, divide by that 3. Or 3y plus 2y cubed. And we're evaluating it, there's a pi there. We're evaluating from y equals -1 to y equals 1. If I stick in 1, this is 3 plus 2. If I stick in -1, I have -3 minus 2. So it looks like I have 5 plus 5. Looks like this is 10 pi. Yeah. So like we wanted between these two functions and these two functions. So this was like when we plotted all 4 lines that we had right here. We plotted all, let me use black. When we plotted all 4 lines, this is what we had. I guess I didn't need x equals 0. So we had a solid shape there. When we plotted all 4 lines, that's what we have. This is what's getting rotated around it. There is a hollow gap in here. So like, if you're looking at the fan idea, I'm going to use not the end, but some region here. The blade doesn't start till here. Like this is the inner radius. And this is the outer, and there's too many ends there. But when we spin this around, we have that and we have that. So this is making a ring, not a circle. As the fan blade spins. So we have, does that make sense? Okay. And this just kind of like lining up which is outer and inner. And it's like outer is from the axis of rotation. We rotated around Y, so like the farthest one out was my outer ring. With practice, it gets easier. You guys ready for another? Okay. Which one looks like the most fun? They're both about as even. See if we can get them both done. So we're gonna do on this example, y equals x squared, y equals x cubed. And those actually intersect, so it makes a region. And rotate around y equals -1, no longer an axis. So, well, before I sketch, let's see where they intersect so we can like zero in where our graph is gonna be. I set them equal to each other, x squared equals x cubed. Do not divide by x squared because that's implying x can't equal 0. And it's clear x can equal 0. 0 squared equals 0 cubed. So don't divide by x. You can subtract the x squared from both sides. You get 0 equals x cubed minus x squared. Factor. And you see they intersect at x equals 0 and x equals 1. And it doesn't matter which one you plug them into, you get a corresponding y value of 0 and 1. So if I'm looking at something like this. Go out that far. Like x squared is like that. X cubed is dipped down below. So we're looking at this region right here. And we want to rotate it around y equals -1, which is down here. Which means it's doing some shit like this. So when we think of the radius, what is really the radius here? We got to do the outer line. Well, radius is going like this. It's going up to there like this. So we have a radius of an outer line. And we have a radius of an inner. The outer line was y equals x squared. And it looks like since we're doing dis, that we're going to have a dx is what we're looking at. So we want things in terms of x. So this is x squared, but it's only x squared from the x-axis. We actually have, it has to go up 1 higher. This value here should add 1 to it. It's actually a little bit easier to say minus the -1 for pictorial. Like if we had a positive y1, you'd just be subtracting the y. So really, we're like subtracting the axis of rotation. So my outer one looks like x squared plus 1. My inner one has that x cubed, but we're gonna subtract the axis of rotation. And we're gonna get y equals x cubed plus 1. And you can see if you redraw these two. X squared, like if this is 1, x squared plus 1 is like that. X cubed plus 1 is like that. Well, it's a little exaggerated there. But that would be revolving around y equals 0 axis, and that looks like the same shape. So subtract the axis of rotation. That's the tricky part. So it looks like we have some shit like this. Oh, fuck. I don't know. But it's hollow on the inside. So we're setting it up. We're doing dx. We saw the boundaries were on x equals 0 and x equals 1. That gives us our limits of integration. We want pi times outer squared minus inner squared. And we want it in terms of x. These are functions of x. So we have the x squared plus 1 is the outer. There's a pi here. X squared plus 1, that's our outer radius. But we have to square it. And then we subtract our inner radius. And we square that. All right, I'm going to pull the pi outside. I'll multiply this crap out. When we have two things, or the sum of two things squared, it's the first one squared plus double the product plus the last one squared. Minus, we'll do the same thing here. The ones go away, right? That's pretty much the only cleanup we have. Then we'll integrate. Bless you. Power divide by a power minus 1/2 x to the 4th. Plug in 1 and all of these are the same. Just 1 times whatever they had. And then we do minus the 0, 1, and we got a lot of zeros here. looks like the common denominator is all of them multiplied together. So 3 times 7 is 21, 5 times 2 is 10. So 21 times 10 is 210. This one is missing the 3, the 7, and the 2. So 21 times 2 is 42. This is the 5, the 7, and 2, which is 70. 2 times 70. Minus the 5, the 3, the 2 is 30. Minus 1/2 of 210 is 105. Let's see, what do we got? 140 minus 30 is 110, minus 105 is 5, plus 42 is 47. Did anyone put that in the calculator and get 47 pi over 210? Ugly, ugly fraction, ugly answer. I'll be honest, on the test, if you got to here and fucked up this part, I'm less worried about it. This is an arithmetic mistake and I do them fucking left and right. I want to make sure you know all the calculus steps. Make sense? I think that's the right.
So
Fuck yeah, boom. I did not fill out the rest of that problem. Actually, I did, and I did it wrong on the paper. I didn't add, I like drew the picture, added the one, but when I did the integral, I didn't have the one there. Which made this problem really easy. It was x squared minus x cubed squared. My integral got a lot simpler. It was completely wrong, but it was simpler. See when you need this out longer? If you do, say something, because I'm taking it. Okay. One more, and then we'll take a break and do the next section. Here, we're gonna do y equals sine x, y equals cosine x. And why don't we do 0 is less than or equal to x, less than or equal to pi over 4. And we will rotate around x. I don't know about you, but I don't remember what the graph looks like up to pi over 4, but I can do pi over 2 pretty easy. So that looks like that'll be -1 later on. Sine x when x equals 0, y is 0, and when x equals pi over 2, sine is 1. So if I connect that in the arc, and we're stopping there, I'll draw that a little thicker. That's my sine x. And cosine, when x equals 0, y is 1, and when x equals pi over 2, y is 0. So it goes like this. And at pi over 4, sine x equals cosine x. So I know this intersects here. So that's my cosine x. So this is the region. And we're gonna rotate it around the x-axis. I only sketch the bottom part because it helps a little bit. If I look at my fan blade that rotates, this is my fan blade here. So is that, it looks like it's gonna make a washer because we have a hollow spot. It's gonna make a ring. It's gonna look some shit like that. Where it looks like cosine x is the outer ring. And sine x is the inner ring. Okay, so we're doing our pi r squared, which is pi y squared. But we're doing y squared like outer minus inner. So pi, but we want in terms of x because this is a dx. So cosine squared x minus sine squared x dx. And we're going from 0 to pi over 4. Anyone recognize what cosine squared x minus sine squared x is? No. It's one when they're added together. This actually has a nice simple form. This is cosine of 2x. This is one of the variations of cosine of 2x. So what's the integral of cosine? Sine. How many of you like go, what's the derivative of? I do that too. I'm like, what would I have to take the derivative of to get it? Because it helps me identify what the sign is going to be. It's easy to remember the signs there. So this is going to be a sine. So we'll have a sine of 2x. But since there's a 2 inside, like the integrating, just like we did with the exponents, we end up dividing by 2. And we're going from x equals 0 to x equals pi over 4. So this is sine of pi over 2 minus sine of 0. And that's just 1 minus 0, right? This just ends up being pi over 2. that make sense? If you don't remember that this is cosine 2x. Since we got a little, like, if you wanna take a break, take a break, we'll start up in 10 minutes, if no one does, we'll start up sooner than that. But like, if you're like, I don't remember this is that. But if you remember. Oh, maybe, I don't know how else you're gonna get to the 2x. Like, this is the one a lot of people remember. Cosine 2x has three forms, actually. It has that form. And then it has variance of this one. If I solve for cosine squared x, I have 1 minus sine squared x. And if I plug that in for cosine squared x, I get 1 minus 2 sine squared x. And if I solve it for sine squared x, I get 1 minus cosine squared x. If I plug that into sine, I would get 2 cosine squared x minus 1. Yeah.
Right there.
Yeah.
Okay, sorry, I came in late, so you might have already said this, but I'm really confused on kind of the methodology, like how the graph relates to the two circles or two ovals.
So. Without being able to do this in 3D, it's a little bit harder, but. What we're doing is we're taking some function. Or two functions, like we're doing some. Area between them. And we're taking this. Like, let's say that's A and that's B. And this is always, all of these in 6.2 and 6.3 involve rotating around an axis. So we're gonna spin this. In something that's in 3D.
Oh, I get it.
Does that make sense?
Yeah, now I get it, that it's 3D makes so much sense, yeah. I get it.
Yeah, this is a three-dimensional thing. That's why, like. I was trying to show like a 3D sketch there.
Oh, I get it.
Oftentimes it's easier to do a side profile. My best 3D sketch was right there. You're gonna get good at drawing 3D shit in Calc 3.
First, I gotta get good at drawing things.
Yeah, you'll be, actually. They kind of go hand in hand. Cause like you're drawing any regular shape. Is like art already, but like now trying to throw in like parabolas and x cubes and shit like that. Weird functions when you're working with, they don't have like nice little normal art shapes. So learning how to like sketch that in 3D is kind of fun. That's where you're going. Calc 3. Instead of x, y, like this is y and this is x. Y goes to the right. X comes out of the page. And Z is up and down. So this is like negative Z back there. Negative Y and negative Z. You have these 3D, three-dimensional axis. That's another semester.
That's art right there. That's like an art class.
That is like an art class. So like if you had like x squared plus z squared equals 1. That's making a circle in the xz plane which is where y equals 0. But it doesn't say anything about y, so this is like a cylinder that goes on for infinity. But then you'll have some boundaries like in the problem. But yeah, you get practice. No point pulling away, people don't. Great.
Question.
Yeah.
When you took the integral of cosine 2x, why didn't you put the 2 in the bottom?
Why did I put the 2?
Yes.
Because like cosine, the integral of cosine x is sine x. I don't have cosine x though. I have cosine 2x. So if you need to do a u sub here, you can. Let's look at that line with the u sub real quick. So pi 0 to pi over 4. I'm just rewriting the problem real quick. I'm going to say u equals 2x. So du equals 2 dx. So divide by 2, I get 1/2 du equals dx. Now there's 2 ways to proceed from here with the u sub. One of them is to just do the u sub, put du in. I'll put the du at the end. And I'm replacing the 2x with a u. I've got cosine of u. And if I want to keep the same length of integration, I very much need to indicate that it is not u. I need to say this is x equals 0 to x equals pi over 4. Or we can figure out what those values are. When x equals 0, u equals 2x, 2 times 0 is also 0. And when x equals pi over 4, u equals 2 times, not pi over 4, pi over, I jumped the gun. Pi over 4, we get pi over 2. So the other way is to redo the limits as 0 to pi over 2. And we have 1/2 cosine u du. And we never need to go back. If I do this one on the left, though, just doing the one on the left, pi over 2, we integrate cosine, we get sine. And we're going from 0 to pi over 4, which is, if I place the u back in, this is in terms of x. So I need to replace the u with the 2x, put the 2x back in, and notice that's what we got. The shortcut way is recognizing that if I started with sine of 2x and I took the derivative, I would have a 2 sine 2x or 2 cosine 2x dx. But I don't have cosine 2x. I don't have 2 cosine 2x. I just have one of these, so I'll divide this by 2. So when I go backwards, cosine 2x, when we integrate cosine 2x dx, you're going to have the 1/2 sine of 2x. If you like the u sub, do the u sub. It does make it quicker to not do it, but it takes practice. It's easy to forget that you all just got out of Calc 1, basically. All right, you guys ready for 6.3 examples? Actually, Let me pause that recording and do a separate recording so that they're separate. Stop recording.